Okay, students, now again we are having system of linear equations here. We are having three equations with three unknowns. So we are going to solve this using matrix approach, but the method is Gauss Jordan elimination method. So I'm going to show you how that can be done. So as usual, don't forget to subscribe the channel and to like and share the channel so that other students can also use it. When I directly dive into solving this one, what comes next is a solution. So the solution goes like this. First, we have to change the given system of linear equations to matrix equation. Okay, so in order to change this to matrix equation, what we need to do is we have to take the coefficient matrices. Okay, so the coefficient matrix, this one is directly obtained from the coefficient of x. So 1 1 1. So we are having here x 1 1 1. And when you come to y, mind you that this is negative 2y, so it needs to be taken to the left. So here 1, and this, when it is taken to the left, it's going to be positive 2, positive 4. So 1 to 4 is going to come for y. And the coefficient for z, here we are having 1, so bring again minus 3z to the left and turns to be positive 3z. So 1, positive 3, and 9 can come. So the coefficients of these variables x, y, and z are taken as you see. Now what comes next is the unknown variable x, y, z, right? The unknown variables x, y, z, they are written in terms of column and matrix form, and then have the constant vector here, those written to the right side of the equality sign, 3, 4, 6, as can be shown. So we got ax equals b4. The method is the Gauss Jordan elimination method. So the next thing that we need to do is have the equivalent augmented form for the given matrix. So the augmented form is going to be a matrix with a coefficient matrix together with the constant matrix. So the coefficient matrix are already labeled here, the constant matrix are already labeled here. So the next thing is to express this resulting this matrix, the augmented matrix, in terms of row echelon form. So let's now try to apply different kinds of row operations and try to change the given matrix in terms of to be written in terms of row echelon form. So look how it has been done. Row 2 is changed as it has been stated here. Row 2 is changed as row 1 minus row 2, so we simply directly subtract 1 minus 1, it is 0, as you see. 1 minus 2 is negative 1, and 1 minus 3, negative 2. 3 minus 4, minus 1, so row 2 is changed, keeping row 1 as it is. Again, row 3 is changed. In order to reduce the step, just row 3 is directly introduced, but you can do this one by one. Now, how is row 3 changed? Simply again subtracting row 3 entries from row 1 entries. So 1 minus 1 is 0 again, and 1 minus 4 is negative 3, 1 minus 9 is negative 8, and 3 minus 6 is minus 3. So you are left with this. Now again, this is not in row echelon form. We have to create a means of making this 0, guys. This 0, this needs to be positive 1, and again this to be positive 1 too. So to do that, what we need to do is this. Now row 1 is changed to, you see, row 1 is changed in such a way. Look. How is that changed? Simply adding row 1 and row 2. So when you add row 1 and row 2, 0 plus 1 turns to be 1, and minus 1 plus 1 is 0, minus 2 plus 1 is minus 1, and minus 1 plus 3 is 2. What about row 3? Row 3 is again changed. How is that done? Multiplying row 2 by negative 3 and adding with row 3. So if you multiply this by negative 3, it turns to be positive 3, so it plus minus 3 is 0. Row 3 is being changed by multiplying this in 3 by negative 3, 6. 6 plus 8, negative 8 is minus 2, and this again, 3 plus minus 3 is 0. So both row 1 and row 3 are changed from this matrix. Now look, it's getting closer to be row echelon form, but there are certain steps left over. So in order to have here, you see students positive 1, let's divide the second row entries by negative 1. So when we do that, look, when we do that, let's multiply the second row by negative. So when you multiply the second row by negative, it's gonna be, all entries are going to be positive. 0, 1, 2, 1. Look, they are written here. So multiple the second entries, the second rows by negative 1. So you are left with 0, 1, 2, 1. And again change the third row by taking negative 1 over 2 of the third row entries. This basically is done because you see here we are having minus 2, so our intention is to make this 1 in order to have row echelon form. So let's multiple the third row increase by negative 1 over 2. You are left with 0, 0, negative 1 over 2 times negative 2 is positive 1, and negative 1 over 2 times 0 is 0. So you are having this. Okay, now look, this is written in terms of row echelon form, students. So your matrix B is now changed to row echelon form. Now let's think of the case where you see the rank of this is going to be. The rank of this matrix, once it is changed to row echelon form, is the number of non-zero rows, right? This is your matrix B, right? This is your matrix B, the augmented form. So if you count number of non-zero rows here, you see the first is non-zero, the second is also non-zero, the third is also non-zero. A non-zero row is nothing but it is a row having at least one entry different from 0. So all these three are non-zero rows. So the rank of this B is, rank of this augmented matrix B is 3. Now let's come to rank of A. When you come to rank of A is nothing but it is the one written to the left of this bar, as you see, which actually this. Again, this is written in terms of row echelon form. The matrix A is written in terms of row echelon form. Let's you count number of non-zero rows for A. Ignore about 2, 1, 0 now. So 1, 2, 3. These are also non-zero rows. So the rank of A is 3 again. The rank of A is the same as the rank of B. And how many unknowns do we have? N representing number of unknowns here. So X, Y, Z. We do have 3 unknowns. So if rank of A is the same as rank of B, and if that is the same as the number of unknowns, as we studied, we have, is according to the Gauss Jordan elimination method, we have, students, a unique solution. That is to say, we have unique values for X, for Y, and for Z, so that this system of linear equations can be satisfied. So the system has a unique solution. What will happen if rank of A is less than rank of B? If rank of A is less than rank of B, we don't have solution at all. What will happen if rank of A is the same as rank of B, and if that is less than the number of variables n? If that happens, we have an infinite number of solutions, students. So we have to understand that. So rank is playing a great role in the case of this discussion. So the above system now turns to be like this. You see, guys, students, look, the above system, the one we obtain here, is directly changed to this one. This is X, this is Y, this is Z, and this is what? These are, see, truth for the constant. So X plus, look, X is here, the coefficient. Y times 0 is 0, so we don't have Y, and Z times negative 1 is negative Z, is equal to 2. X times 0 is 0, so we don't have X here. Y times 1 is Y, as you see, plus 2 times Z is 2Z, equals 1. X times 0 is 0, Y times 0 is 0, Z times 1 is Z, is equal to 0. So what you need to do is you have to use a backward substitution. The value of Z is already known. If Z is known, students, we can use backward substitution. We simply put 0 here, and then you can know what Y is going to be. Clearly, if Z is 0, 2 times 0 is 0, 0 plus Y is Y, Y is 1, right? So if Z is 0, Y is 1, now you can know what X is going to be. Look, Z is already 0, so X minus 0 is X, so your X is going to be 2. So as it has been stated here, our values are Z0, Y1, X2. So dear students, you have now solved the given systems of linear equations, but before you accept that this is the right one, actually it is the right one, but you have to confirm by substituting, right? It says, for instance, X plus Y plus Z3. So do you think that the sum of all these three obtained values makes 3? Yes, 0 plus 1 plus 2 makes 3. So in doing so, please try to check the remaining two equations. I hope the Gauss Jordan elimination method is very, very clear for you. Thank you.